Hello and good morning everyone. Today inshallah we will talk about a very important topic. We will go to constraint optimality. In the previous sessions we already initiated the process of having an optimality in the case of unconstrained optimality or the unconstrained case, in which we used the principles of derivative as we had previously in order to determine the local optima, either maximum or minimum. In this session, besides going through constrained optimality, we will go also how to identify or determine the absolute optimality or the global optimality. Once more, we have local optimality, global optimality, and then we will go to the cases of the constrained optimality. We will talk about the constrained equality constraints in specific in this lecture. For the inequalities and their analysis, I believe you will go through them in operation research down the road. But we are not going to go through the optimality using inequalities. I will leave it to the operation research course. So, I want you to remember, in order to determine the extreme points of multivariable function, in the case it's not constrained, if you remember, these steps are really very important. The first step, of course, is to compute the partial derivatives. Okay. The second step is to put your partial derivatives equal to 0. Sometimes people will tell you evaluate the gradient factor, then put the gradient factor equal to 0. They are both the same. So I'm getting the first partial derivatives because we are talking, as I told you, with a multivariable function. The case that I'm going to discuss with you, it is the simplest of them, which is functions in x and y. So the second step is to find your critical points, which is going to be really very easy. Just getting the first derivative, equating them equal to 0, and then we will be able to get the critical points of our work. So the solution x naught y naught are the critical points. If this is a critical point, then I will go to the second or to the higher derivative. So I will need to evaluate the second order derivative. So I will differentiate the first derivatives. As you know, this is the first partial derivative, so the second will be partial 2f partial x squared, partial 2f partial y squared, and of course you have the mixed derivative, which is partial 2f partial x partial y, or partial 2f partial y partial x. So that's the step of computing the second partial derivatives. Once you already have them, you will be able to find the Hessian matrix, which is, this is our Hessian matrix. You will find f double x, f double y on the principal diagonal, and then f of xy, f of y of x on the secondary diagonal. I will need to evaluate the determinant of this Hessian matrix. And the determinant is really very simple. What I have to do is to get the value of the elements on the principal diagonal minus the value on the secondary diagonal. And this is called the determinant or D value. Based on the value of the D and the value of f double x, I will be able to classify the type of my optimality, as you know previously, of course. The last lecture covered all of this. So, if D is greater than 0 and f double x is greater than 0, it means the second derivative of the function with respect to x is greater than 0 at your point, then you will have local minimum. And if you have D is greater than 0, but f double x is less than 0, then you will have local maximum. Of course, if D is negative, you will have a certain point. If D is equal to 0, the test is inclusive, and we will go to the next step or further investigation in order to investigate this point, if it is a saddle point or it is going to be an optimality point. I believe this slide summarized the main steps that we usually do in order to find or to search for the probable local optimality. If we want to go further and finding absolute extrema or finding global optimal points, in this case, I will add to the previous steps some new steps. So the beginning, in order to find an absolute extrema in the interior of your domain. If the domain interior and the area is not compact, what's the meaning of compact if you remember topology? It means it's not closed or it's not bounded. So our talk here, it's about the compact areas in order to find an absolute maximum or minimum. So if a differentiable two-variable function has an absolute extrema at an interior point, it will be one of your global points. Okay? So if it's a domain, then extrema occurs at a critical point. Type, if it is closed, Weierstrass theory states the following. If you have a function that's differential and continuous, and it is on a closed interval or closed domain, then it must have an absolute maximum value and an absolute minimum value. This is what Weierstrass theory tells us. So once more, the theorem, let the domain is a subset from R2 and the F is such that from D into R. D is a compact. Compact means closed and bounded. And F is a continuous in D. Then F has both absolute maximum and absolute minimum belongs to its domain. So remark that we have two cases. If the domain is compact, if the domain is not compact. If the domain is not compact and you applied the search for the local maximum minimum, then the absolute will be one of them. If your domain is compacted, then the same style, in order to identify the interior points, okay, it's not enough to find the absolute or the maximum. I will have to study the case at the boundary. So I will have to do both steps. In this slide, he will explain to you how to find your extreme points, okay, in a compact set. So how do you find the absolute extrema of a continuous function in a compact set? Find the critical points that lie inside the set in R, in which I will get the first order derivative, making it equal to 0, getting the second order derivative, evaluating the determinant of the Hessian matrix according to the previous steps. Okay? The second step, find all the boundary points at which are probable to be points on the contour. Then I will find the value of the function at the boundary. You identify the boundary of your domain. Then start finding the extreme points. Calculate the value of the function, the value of the main function, at the critical points from the global analysis and at the boundary points. The maximum of them is going to be the absolute maximum value, and the lower value of them, it is the absolute minimum value of your function. These are the main steps of finding an absolute optimum points. This is very, very important. Okay? I've shared all of this with you in two records. One of them was recorded in the previous year with your companions. Also, I don't remember if I shared this or not, but I shared the other one, which was recorded from my office at home. Okay? And also you will have a record for this session. So restricted, absolute, and relative extrema. But in this case, I will talk with you about the constraint. This is the constraint optimality. Focus. In the previous slides, in the previous two slides, we were talking about having a domain, either an open domain, and I'm searching for the local, and which one of them is the optimal. Okay? This will go with the general case. Find the first derivative, what the first derivative equal to 0, get critical points, blah, blah, blah. That's what explained in the previous session and in the previous slide. If your domain, Farid, is closed, is compact, means it is closed and bounded, then determine first the interior probable points, and then determine the boundary points, substitute in your function, and from this point start to identify the highest value of your function is going to be the absolute maximum. The lowest is going to be the absolute minimum, or the global maximum and the global minimum. They are the same. But in this case, what we are going to do starting from now till the end of our lecture today, we will try to search for the best solution or the optimality, but with a condition, an external condition. Okay? This condition that will be given, it is how to find an optimal solution for your problem on a certain curve, under certain condition. So now I will talk about the constraint optimality as I told you. So maximizing or minimizing a function f of x, not on the whole domain, no, but subject to the constraint g of xy equal to 0. And the same applies for the 3-dimension. So I want to have a function which is f, I want to find the maximum and minimum, but not in anywhere in its domain, in a specific on a certain curve belongs to this domain. This is going to be explained really very easy once you look to this case. If this is your domain, and that's the boundary, that's the J, which is the curve I want to study the optimality on. So now I know one of the points that's shared between this curve and the region or the domain of function, of this function, will contain x naught, y naught, which is the optimality point that I'm searching for. In the previous sessions or in the previous cases, I was studying the optimality of the objective function, just only one function. But now I will study the optimality on a function, but in a specific, on a certain curve. Okay. So it's really very simple. So once more, as I told you, we say that f has an x naught and y naught, belongs to its domain. An absolute maximum or minimum restricted to the curve, just only on the curve, g of xy equal to 0. F, for f x naught y naught, it is the largest or the smallest, the largest is the maximum, smallest is the minimum, value of f on the same segment of this curve, which is explained by this equation. Had extended to both sides of the points x naught and y naught. So, which means I will have the optimality, but not on the whole domain, just on a specific curve. Okay, as I told you, these are the cases for the constrained optimality. The main condition is to have the gradient vector for the curve doesn't equal to 0, and the steps, the method that we will use, it's called the Lagrange multiplier, which is really a very simple idea. The main issue, I will find the gradient vector of the objective function, or the main function, and the gradient vector of the constraint, or the condition, or the curve, okay? And I will equate each one of them times lambda, because simply they are parallel to each other. And we know if we have two directions parallel to each other, there will be a percentage between them, or a scaling between them, or a ratio between them, okay? This is the general case. So the idea is coming from the derivative. The idea is coming from the gradient vector, okay? So all I have to do, the steps is really very simple. All I have to do is to get the gradient vector of the function, the gradient vector of the curve. I will equate them, but multiplied by lambda, because in general, they are not equal to each other, but there is a percentage between them, okay? In such a case, I will need to find the conditions that will make this equation to happen, and the points and studying at these conditions will give me the optimality belongs to this curve and having the maximum or minimum on the main curve. I believe if we discuss this as a steps on more than one problem, it will be easier for you. Okay, let's go through this problem. He wants you to find the maximum and the minimum points on the given function f of xy equal x times y, and subject to the constraint x squared plus y squared equal to 1. So I need to maximize or minimize the value of the function, which is f of which equal to x times y. But just only on the points of the circle, which is x squared plus y squared equal to 1 over the unit circle. Okay, done. I will use, now I have a constrained optimality. This is how to generalize, how to identify your problem. And I will start by, first of all, trying to put both functions in the shape that I can use in order to find the gradient vector. So I will try to put the condition on an equal 0 equation form. So instead of dealing with x squared plus y squared equal to 1, I will put it x squared plus y squared minus 1 equal to 0. This step is important because in some functions or in some conditions, Farid, you may find x squared plus y squared equals z. No, I don't want it in this shape. I want it to be x squared plus y squared minus z equal to 0. Do you understand what I'm saying? Because this is going to have an effect on you once you are trying to evaluate your gradient vector. But in this case, it will have no effect because already the number is on the right side. But to generalize the steps, let's put it equal to 0. So the function or the condition is x squared plus y squared minus 1. I will need to evaluate the gradient vector for g, and easily I can get the gradient vector for f. Of course, you remember what's the gradient vector. The gradient vector is simply, I will need to differentiate the gradient vector for f. So very simple. Get the derivative, so it's partial f, partial x, partial f, partial y. Do exactly the same for the condition. So getting your gradient vector, which is gonna be partial g, partial x, partial g, partial y. Then both them equal to each other and multiply the second by lambda. So the slides are really, and the steps are really well written. So first of all, I will try to get the gradients. The gradient vector for x times y, it's gonna be y. The second coordinate is differentiating with respect to y, which is gonna be x. So that's actually the gradient vector for the first function. Differentiating with respect to x will leave you with y. Differentiating with y will leave you with x. Do exactly the same with the second function or with the condition. Okay? So differentiating x squared, okay, it's gonna be a 2 over x. Differentiating y squared, it's gonna be a 2 over y. Now I have the two gradient vectors. I will let one of them equal to lambda times the other gradient vector. So the next step, as you can see, the Lagrange system. The gradient vector of f is equal to lambda times the gradient vector of g. What's lambda? Just a number. Okay, it's a number belongs to the real set. Okay, so the next step is to try to expand them. Of course, as you can see, it's gonna be y equal to lambda times 2x. It's gonna be x equal to lambda times 2y, which means you have two equations. But actually, you have more than two equations, Farid. You have those two conditions, plus that the points should exist on the condition, which is x squared plus y squared equal to 1. So actually, I have how many equations? 3 of them. 2 from the gradient vector, and the third one from the condition that you should reserve. And be sure that it is correct at all times. Okay? Okay. The problem, till the time being, you will have no problem whatsoever. It's really very simple. Then find the function, finding the gradient vectors, equating them both together. Then the next step is to try to solve the system. Unfortunately, these equations are not linear equations. They are non-linear equations. And they will need you to think a little bit and to solve more than one problem in order to get the skill of solving these problems or playing with them. Okay? How to substitute from one into another and how to check your results. So it's very major. So all I have to do at the time being, solve the system from 1 and 2. I will start solving this system. The second step, okay, in order to solve this system, Okay, I have the first equation, which is y equal to 2 lambda of x. The second equation, x is equal to lambda of y. It seems a really very nice idea if we substitute from the first condition into the second condition. So once more, I would substitute from the first into the second equation. How to do this substitution? I will replace y by the value which is 2 lambda of x, which means I will have the following. I will have x equal to 2 lambda times 2 lambda of x, which means it's going to be 4 lambda squared x. Yes, Mr. Farid, I will move them all in one side. So the next step, Ziad, I will have x minus 4 lambda squared of x. Take x as a common and equate equal to 0. Okay, Mr. Farid, now look to the alternatives. It is giving you either x equal to 0 or 1 minus 4 lambda squared equal to 0. Am I right? You have just only two options. صح, Mr. Ziad? So for the first of them, if x is equal to 0, if I have x equal to 0. Now I have one of them. If I took x equal to 0 and substitute in this equation, it will give you y equal to 0. Is this an acceptable solution for this problem or not? How to be sure about this? I will take these two values in my hand and I will go to the condition. Let's substitute together. 0 to the power of 2, 0. Plus 0 to the power of 2, which means 0 equal to 1. That's a contradiction, of course. Okay, how 0 on the right hand side equal to 1? So this is not the correct answer. So I will eliminate or reject this this case. I will go to the other case. What's the other case? That 1 minus 4 lambda squared is equal to 0. So now I will study that 1 minus 4 lambda squared equal to 0. This is very, very simple. If I have 1 minus 4 over lambda squared equal to 0, this means 4 over lambda squared is equal to 1, which leads to lambda squared is equal to 1 over 4. That leads to lambdas equal to positive or negative 1 over 2. So now I have the option of using this relation as you saw. So we came to the point that lambda equal to plus or minus half. What am I going to do? I have the value of lambda. So I will try to test my waters. I will take lambda and start substituting in these two equations, which you will be in between. Okay, let's substitute together. Y equal to 2, and the lambda is positive to half. So which means y is equal to x. That's an alternative. Okay, if y is equal to x, all I have to do is to substitute in the condition variable. So I will replace y by x. So it's going to be 2x squared equal to 1, which means x squared is equal to 1 over 2, which leads to x is equal to positive or negative half. So once more, if lambda is equal to half, that means y is equal to x. Let's substitute in the constraint that we have x squared equal to 1. And as I told you, you will have x is equal to positive or negative 1 over root 2. In a similar manner, once x is equal to y, you will equate the value of y. So my points are 1 over root 2 and 1 over root 2, or negative 1 over root 2 and negative 1 over root 2. Those are the probable cases. But there is a case I didn't study. I studied the case if lambda is equal to positive half. What if lambda is equal to negative half? I believe it will be the same, but the only thing it will be that x is not equal to y, y is equal to negative of x. So now I will try to solve with the substitution with the same steps, but once you have x 1 positive or negative 1 over root 2, then y will be negative 1 over root 2, which means if x is 1 over root 2, y is going to be negative 1 over root 2. If x is negative 1 over root 2, y is going to be 1 over root 2. This is the case that I'm telling you about, and once you substitute, you will have your points. That's the first case, and those are the second cases. This is for lambda equal to half, and that's for the lambda equal to negative half. I have probable 4 values. For each one of them, I've substituted in the value of the main function, of the given function, that's required to find the maximum and the minimum. The largest is going to be relative to the maximum point, the maximum value of f, which means this is going to be an extremum point, and the lowest, it is going to be the minimum. So now, according to this discussion, the points with optimality on this function satisfying this condition, the maximum value will be half, and the lower or the minimum value will be negative half. I want you to summarize the steps once more in your head. It's really very simple. It's really very simple. What we did, try to memorize. Getting the gradient vectors of the function and the constraint. Then, Mr. Farid, I will equate both of them together. This will leave me with the system of equations, but don't forget, plus the constraint. Try to play with your equations a little bit in order to find possible cases of solution. Study each case of these cases, but first check the constraint. If it is okay, then continue. If it is not, then reject the solution. After that, you will have a bunch of points, substitute in your function. The largest of them is going to be relative to the maximum point. The lower value is going to be the minimum point. It's really very simple. And it is guaranteed to have them in your exam. Okay, let's look to this problem also. He wants you to figure the figure. He gives you a figure, but I don't think he need to give you a figure, because he stated that the intersection of the elliptic paraboloid, also he shouldn't say elliptic paraboloid, because you know this equation, it's an equation for an elliptic paraboloid. Am I right? So this is what we studied in the previous part. This is z equal to x squared plus 4y squared. So it doesn't have to, but you know. And the right circular cylinder, also I know if I have an equation in given in 2 variables, but I'm in 3 dimensions, then probably this is going to be one of the cylinders. So x squared plus y squared equal to 1, that's a circle. But if in 3 dimensions it's going to be a cylinder, so it's really very nice. Now I have a paraboloid, and embedded in it there is a cylinder. I need to find, okay, the optimality on this curve. So he wants you, okay, to use Lagrange. He shouldn't also, he should leave it to you, Lagrange multipliers, to determine the highest and lowest points of the intersection curve. Remark. So he is gathering in this problem your knowledge about the surfaces and the intersection, which is probably a curve. And if you remember my words previously, when we were taking these intersections and talking about the level curve, do you remember? Okay, I told you you will need them in this part. So once more, okay, that's the function required to be optimized, which is z equal to x squared 4y squared, subject to the constraint. The constraint is x squared plus y squared equal to 1. Why I said this is the constraint? Because by logic, the diameter of the cylinder is fixed. But the diameter of the level curves of your function, it's spreading. It's a paraboloid, you know, you understand what I'm talking about. This is a paraboloid, of course. This is the case of, as you can see, if this is x, that's y, and that's the z. That's the paraboloid that we are talking about. See, it's the level curves, it's circles, but what's happening with these circles? They are increasing, am I right, Mr. Farid? While the function x squared, the cylinder, it is with fixed diameter, it's a unit circle, and it's gonna be a cylinder, so that's the shape that's gonna evolve that you will see. And I need the intersection, so the intersection will be this level, this circle, not in by 1, but the level of the x squared plus y squared equal to 1 somewhere in the paraboloid, okay? I believe the shape in 3 dimension will transfer this issue very well. That's the paraboloid, as you can see, Miss Nada, that's the paraboloid coming out of the 0 and start opening. And that's the cylinder inside it, that goes, the part that will contain the intersection is the unit circle. So now I identify the function to be optimized and the condition, which is the circle, as you can see. Now I will move to the steps once more. The first step, what to do, Ziad? Evaluating the gradient vectors. So I will start by compute the gradients. I will evaluate the gradient vector for both equations. What's the gradient vector, Miss Nada, for this equation? I will differentiate with respect to x, which is going to be a 2 over x. I will differentiate with respect to y, which is going to be 8 of y, as you can see. I will differentiate this function with respect to x, which is going to be 2 over x. I will differentiate this function with respect to y, which is going to be 2y. So I got the gradient vector for both of them. Then I will equate each of them together, but don't forget multiplying by the value of lambda or the Lagrange multiplier. So the next step is to set up the condition. The gradient vector of f is equal to lambda times the gradient vector of g, where lambda is just only an arbitrary constant. Okay, I need to identify the value of Lagrange. Okay, of this lambda is called the Lagrangian. Okay, the second step is to start to substitute in these equations. So the first is it's gonna be 2x equal to lambda 2x. 8y is equal to certain lambda times 2y. But don't forget, with these equations, I will have to satisfy the constraint. So I'm looking for a probable solution for these two equations that satisfy this equation. I'm trying to solve those, but satisfying this condition. Okay, let's think about probable solutions. The first is stating that 2x is equal to 2x and 8y is equal to lambda 2y. We will have various cases based on the equations. The first case, let's consider that x doesn't equal to 0 and y doesn't equal to 0. Both of them not equal to zeros. And then, according to this, I can divide the first equation on x, which will leave you, okay, for lambdas equal to 1. Okay? And for the second equation, if you try to substitute with your lambda into the second equation, it's not going to be satisfied. If I did the same, dividing on y to both sides, you will end up having lambda from this case is equal to, or if I substitute with lambda is equal to 1, I will have 8y equal to y, which is going to be 6y equal to 0, which means y is equal to 0. This contradiction or contradicts my assumption. So this contradiction means x equal to 0 or y equal to 0. Okay? So once more, I will try to study the case. Not both of them are equal to zeros, but just only one of them is equal to 0. So I will go to this case if I substitute that x is equal to 0, and I will discuss this case in the constraint. If I put x equal to 0, which means y squared equal to 1, and this will leave you with y positive or negative 1. In this case, the points will be 0, 1, and 0, and negative 2. I'm sorry, 0 and 1, x is equal to 0, and the possible y's are positive 1 and the negative 1. In a similar manner, then from the constraint that z is equal to x squared plus 4y squared, the function values relative to these two values are equal to 4. I will repeat the same, considering y is equal to 0 and substituting then in the constraint, and then I will have x squared equal to 1, which means x is equal to positive or negative 1. Take this value, because you will have at this time, or in this case, you will have 2 points, which is positive 1 and 0 or negative 1 and 0. These are the 2 points. substituting with these 2 points in the value of your function, not the constraint, the value of your function, then the probable value is going to be positive 1, as you can see. From this, the largest is going to be the maximum point, the lowest will be the minimum point, as you can see. So the conclusion, maximum value for the function, the value of f is going to be 4, and it will happen at 0, 1 and 0, negative 1. And the minimum values is going to be 1, and it will happen at 1 and 0, or negative 1 and 0. So once more, in this problem, you already have your function, and then you will have your constraint, and the same steps. I've also added more problems. As you can see, this is also a very nice problem. We want you to find the critical points of the function 4x squared plus 6y squared and z, which is, Ms. Nada, what's the equation if you remember? Z equal 4x squared plus 6y squared? Yes, you are right, of course. It's an elliptic paraboloid, okay? Because you have two axes to the power of 2, or 2 variable coordinates with power 2. One of them is with no power, okay? And this will happen with elliptic paraboloid. We all subject to the constraint, Mr. Farid, x squared plus 2y squared plus 4z squared minus 40 equal to 0. And that's an equation, if you remember, yes, it is for an ellipsoid. Okay? The ellipsoid اللي هو بطيخة يعني، ماشي؟ Okay. طبعا 1, 2, 4 equal to 4. طبعا I want you to remark that sometimes we put 4z squared on the other side. Don't use it this way. You should have them all in one side, okay? In order to evaluate the gradient vector. And also for the elliptic paraboloid that's given to you, before you start evaluating the gradient vector, please put the equation equal to 0. This is really major, okay? Because it will make a difference in the sign. Okay, he wants you to use the Lagrange multiplier in order blah, 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 blah. So I need to maximize this, the points on this function, but under the condition that they belong to this ellipsoid, to that sphere. Same treatment. I will start with the following. First, get the gradient vector, solve the system of equation, discuss the alternatives, check in all times, check your constraint, then finally choose the maximum and the minimum points. Let's do it together. Set up the gradients.